What's up, everybody? Got another video here for you. This one is business calculus. It's the definite integral and the fundamental theorem of calculus. So this is a pretty good one. All right, so let's look at this. We won't spend too much time on this part of it. We'll get into we'll work one example with this, and then we'll get into the evaluating the integrals. So it says, let f of x be continuous and satisfy f of x is positive on the interval a to b. Then the region under the curve y equals f of x over the interval a to b has area a equals the limit of f of x1 plus f of x2 all the way to plus f of x2. And all that, once you add that up, times delta x. And we do that as n goes to infinity, where x sub j is the left endpoint of the jth subinterval if the interval a to b is divided into n equal parts, each of length delta x over b minus a. Delta x equals b minus a over n. All right, so basically what we're doing is we're taking the area that we're trying to find, and we're breaking it up into rectangles, and we're finding the area of those rectangles and summing up those areas. And so, as you know, the area of a rectangle is length times width. Okay, so I'll explain that more when we get to the working the example. I'll explain this more, what that means. All right, so let's look at the example. It says, let R be the region under the graph f of x equals 2x plus 1 over the interval 1 to 3. Compute the area of R using 6 subintervals. So we're going to use 6 rectangles. So the first thing we need to do is we need to graph this thing. All right, so we got 1, 2, 3. 1, 2, 3, something like that. So if we graph 2x plus 1 has a y-intercept of 1, we go up 2 and over 1. So it's going to look something like that. And we have our graph here. And I'm going to erase these little tick marks. All right. So this is 1. And we're looking to find this area here. And we want to break it up into 6 rectangles. Let's see how many we got. 1, 2, 3, 4, 5, and 6. So this will be 3 right there. Okay, so we're going from 1 to 3, and we're using left endpoints. And what they mean by left endpoints is we've got a rectangle here, 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 and here. There's our rectangles. All right, so what we need to do is we need to get the width of these rectangles. The widths are going to be the same. So the width is delta x is equal to b minus a, so 3 minus 1, over the number of rectangles we have, which is 6. So that's going to be 2 over, that's going to be 2 over 6, which is 1/3. And so what we do now is we take the 1/3 and we add it to 1, and that's going to give us 4/3. And then 4/3 plus 1/3 is 5/3. 5/3 plus 1/3 is 6 over 3, which is 2. And then 2 plus 1/3 is 7/3, and 7/3 plus 1/3 is 8/3. All right, and we know that the width of each one of these rectangles is 1/3. All the widths are the same. All right, so now let's look at this. So let's just look at this first rectangle here, and then that will apply to each one of will apply to the rest of the rectangles. So we've got the width of this rectangle, which is 1/3. Now we need the height of it. So would you agree that the height is just the y value? See, it's just the y value is the height. So how do we find that y value? Well, this height here, see, if we pull that over to the y-axis, that height would just be f of 1. We would take the 1 here, plug it into our function. See, our function is f of x equals 2x plus 1. So if we take the 1 and we plug it in, that's going to give us a height of 3. And so the area of this rectangle would be 1/3 times 3. Okay? And, well, it gives us 3, but it would be 1/3 times f of 1. And the height of this rectangle would be the width, which is 1/3 times f of 4/3, and so on. But see, what they're doing here is, see, our 1/3, so pretend like this is our 1/3, this is our f of 1, f of 4/3 plus, and so on. So they're delta x is being multiplied by each of these heights here. But what they're doing is they're just taking that width and they're pulling it out. And so they're just summing up the heights and then multiplying by the width. And so what we can do here is we can say that the area is equal to 1/3 times f of 1 plus, see, that's the f of 1 plus f of 4/3 plus f of 5/3 plus f of 2 plus f of 7/3 plus f of, I'm running out of room, plus f of 8/3. And that's going to probably be off the screen. And so now I get the area is 1/3 times, and now I've got to take each one of these values here, plug them into our function here. So I'm going to plug the 1 in, that's going to give me 3. Then I plug the 4/3 in, that's going to give me 11/3. Plug in the 5/3, that's going to give me 13/3. Plug in the 2, that's going to give me 5. Plug in 7/3, that is going to give me 17/3. And then plug in the 8/3, that's going to give me 19/3. And once you add all that up, multiply by 1/3, you get 9.333, approximately that. Okay. So for instance, for this one right here, we're just doing f of 4/3 is equal to 2 times 4/3 plus 1. And we're evaluating that, and that's how we get the 11/3. And you just do that for each one. Okay, so, you know, as far as this goes, when you're finding the area under a curve, you're not really going to do it like this, breaking it up into rectangles. And the idea behind this is the more rectangles you use, the more accurate your area is going to be. And you can see here, this area, this is just an approximation. It's not the exact area under the curve, because you can see these little gaps here. Okay, so the area that we found is actually less than the actual area. And so, you know, when you look at this, you might think, well, there's an easier way to do this. You know, if we look at this and we're looking to find this area from 1 to 3, you know, if we draw that up there, you know, yeah, you can just cut it here, find the area of that triangle, find the area of that rectangle there, add those areas up, and you have the exact area, and that's true. But this is just an example to show you how we can approximate the area, because sometimes this side here may not be straight. Okay, instead of being a straight line, you may have something like this, like a curved line. And then how are you going to find that area? Well, you can approximate it. And then what this is saying is, okay, so what we can do is we can take this and we can sum up. N represents the number of rectangles, so we can sum up an infinite number of rectangles. See, we're taking the limit as n goes to infinity. We're not, in the business calculus, we're not really getting into a lot of detail like we would in a regular calculus class. Okay, but I'm just kind of trying to give you the idea of what's going on here. All right, so we've got the fundamental theorem of calculus. If the function f of x is continuous on the interval a to b, then the integral from a to b f of x dx is equal to capital F of b minus capital F of a, where capital F of x is any antiderivative of f of x on a to b. So basically what we're doing is we're integrating it, and then once we integrate it, we're doing our antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. So let's do some examples here. All right, so we need to integrate this thing, and in order to do that, the first thing we need to do, we've got e to the negative x plus, we're going to rewrite that square root as x to the 1/2. And so we're going to get e to the negative x, and remember, now we've done this already in previous videos. When you integrate e to the negative x, it's just e to the, or whenever you integrate e to a power, it's e to that power times the reciprocal of the number in front of x. So the number in front of x is -1, and then if you take -1 and you flip that, that would be 1 over -1, which is just -1. And so we've got a -1 in front. That's the antiderivative of e to the negative x. And then for this one, that's going to be x to the 3/2, add 1, multiply by the reciprocal of your new exponent, and then we're evaluating that from 0 to 1. And so this would be -e to the -1 plus 2/3 times 1 to the 3/2. Okay, so we plug the 1 in, minus, and then we plug the 0 in. That is -e to the -0 plus 2/3 times 0 to the 3/2. Okay, and make sure when you plug the 0 in, you're subtracting the whole thing. So put this whole thing in a bracket so you know it's minus that whole thing. And so this is going to give us -1 over e, right? This is over 1, and we can take this and move it to the denominator, and that changes the sign of the exponent. It changes it from a -1 to a +1. And remember, if we don't write anything there, it's understood to be +1. And that's going to be plus 2/3, because 1 to the 3/2 is 1. 1 times 2/3 is 2/3. And then that's going to be minus -1. E to the 0 is 1. And then this is just going to be 0 plus 0. And so we get -1 over e plus 2/3 plus 1, which is, let's see, that's going to be 5/3 minus 1 over e. And that is about 1.299. And you know, the other thing you can do, once you get all this plugged in right here, I mean, you can punch that into your calculator, but I'm just kind of simplifying it without a calculator and then plugging it in. If you go to this, that's fine. If you don't, that's fine. You can just take your calculator, plug all that in, and get the 1.299. At least you can if you're in my class. Okay. All right. Let's look at the next one. All right, so let's integrate. So the antiderivative of 1 over x, that's natural log, absolute value of x, minus, and then that's x cubed times the reciprocal of the new exponent, and then we're going from 1 to 4. So we've got to plug the 4 in, so that's going to be natural log 4 minus 1/3 times 4 cubed, minus, and now we're going to put all of that in bracket because we're going to plug the 1 in. That's natural log 1 minus 1/3 times 1 cubed. And you might be thinking, well, you've got absolute value on natural log. How come you aren't putting absolute value here when you're doing natural log 4 and natural log 1? Well, because I don't need to, because 4 and 1 are positive. Now, if it was like -1 and -4, then I would need to bring the absolute value with me. And so this is going to be natural log 4 minus 4 cubed is 64, so that's 64 over 3, minus, and natural log of 1 is 0, minus 1/3. And so that's going to be natural log 4 minus 64 over 3 plus 1/3. And so that's going to be negative 63 over 3. I will write it out. So that's natural log 4 minus 63 over 3, which is natural log 4 minus 21. And so this is going to give us negative 19.6137. And there's your answer. All right. So you see, it's not that bad. The most complicated part, well, I mean, integrating them may get kind of tricky on some of them, but for the most part, just make sure you're careful when you're plugging that into your calculator. Okay, I mean, you can just plug that in if you want to, or you can go to this step and then plug it in, or down to here and then plug it in. Up to you. All right. All right, so let's look at this one. So we've covered integrating, okay, and we've covered integrating stuff, doing U substitution. And this is one where we would need a U substitution. So the first thing I'm going to do is I'm going to take the 8, and I talked about this in the previous videos. We're going to pull the 8 out. And remember, we're going to pull the 8 out because if we let u equal x squared plus 1, then du is 2x dx. And you can see that the 2 here does not match that 8. So I'm going to pull the 8 out. So you can see here, and I'm not going to go over this u substitution very much because I went over this in detail in the previous video. Okay. So you can see we've got the x dx, but we need a 2. So we need to multiply by 2. So that means we need to come outside and divide by 2. And so this is going to be 4 times the integral. And the x squared plus 1, I'm going to replace that with u. So that's u cubed. And then the 2x dx, I'm going to replace with du. And then I'm going to go from 1 to 2. All right. Now, you might be thinking, 1 to 2, I thought it was from 0 to 1. Well, it is 0 to 1. But what happened? Well, if you look at this, our original problem is in terms of x. So these bounds here on your integral, those are x values. But what did we do? We changed our variable to u, so our bounds need to be u values. Okay, so how do we get that? Well, u is equal to what? 0 squared plus 1, and u is equal to 1 squared plus 1. So this is 1 and this is 2. So what I did is I took each one of these bounds here and I plugged them into here to get my u values. Okay, and so now that's going to give us 4, that 4 there, and then that's u to the 4th times the reciprocal of the new exponent, and then that's 1 to 2. And so that's going to give us u to the 4th from 1 to 2, which is 2 to the 4th minus 1 to the 4th. So that's 16 minus 1, which is 15. Okay. Now, you might be asking yourself, and I'm going to go over it in this problem. Okay, I'm going to spend a little time to show you about changing your limits of integration, like what we did here with the 1 and the 2. Do you have to do that? No, you don't have to. But let me show you. So let's just say that we got here and we said, okay, I'm going to leave it as 0 and 1. I'm not going to change my limits. So that would give us 4 times 1/4 u to the 4th from 0 to 1, which is equal to x squared plus 1 to the 4th from 0 to 1. So, because the 4 times 1/4 is 1, and I'm just left with u to the 4th. And what I've got to do, if I leave my bounds on my integral as 0 and 1, the x values, I've got to plug this x squared plus 1, I've got to put it back in for u. Okay, so you don't have to change them, but remember, if you don't, you have to get it back in terms of x. You've got to replace this with x squared plus 1. And so what that's going to do, that's then going to give you 1 squared plus 1 to the 4th minus 0 squared plus 1 to the 4th. We're going to plug the 1 in, then the 0 in. And that's going to give us 2 to the 4th minus 1 to the 4th. Okay? And that, you can see, that's going to give us the 15. Now, look, to me, it's much easier to change the bounds on your integral, because you see this part right here. You see this part right here and this part right here. I just did it here. See, I'm just doing it up here and just changing my limits. Because, see, we end up with 2 to the 4th and 1 to the 4th anyway. I'm just doing it here instead of here. I think it keeps it simpler. It's not so cluttered up. I mean, this one really isn't that bad, but they can get nasty. When you get it back in terms of x, you keep your bounds the same on your integral. So if I were you, I would make the substitution. Just change your limits. Change the bounds on your integral. Okay? I mean, but like I said, you don't have to, but if you don't, just make sure after you integrate, you get it back in terms of x. But it's just easy. To me, it's easier just to do this. All right, let's go to the next one. Well, I left off the dx in the problem. All right, so here we've got another integral. This is going to be u substitution. And look, if you don't see it, that's going to be 1/4 to 2, and that's going to be natural log x times 1 over x dx. We can separate them, okay? If we multiply this back, we get natural log of x over x. I worked a problem similar to this in the last video, went into a lot more detail. See, at this point, all we're doing is learning what do we do with these numbers on the integral? That's all we're learning. We've already learned how to integrate. Okay, so this video assumes you know how to integrate already. All right, so I'm going to let u equal natural log x, and so du is 1 over x dx. And so this is going to be the integral u du. The natural log of x is getting replaced with u, and then the 1 over x dx, see the 1 over x dx, that's du, so I replace it with du. Now let's change our bounds. So I've got u equals natural log 2 and u equals natural log 1/4. So we're going from natural log 1/4 to natural log 2. And so if we integrate, we're going to get 1/2 u squared from natural log 1/4 to natural log 2. Okay. All right. So this is going to give me 1/2 times, and that's going to be natural log 2 squared minus natural log 1/4 squared. And for this one, just throw that into your calculator, and you should get negative 0.721. All right. Now notice I left the 1/2 outside here. Look, this right here could also be written 1/2 natural log 2 squared minus 1/2 natural log 1/4 squared. It's the same thing. It's all I did. I just left the 1/2 out. See, it's just like you're taking that 1/2 and factoring it out. I just think it's easier to do this. Then what you can do is you can just subtract these two and then multiply by 1/2 instead of doing 1/2 times this minus 1/2 times that. Okay, just leave the leave the coefficient outside the brackets there. All right, so here it says use the fundamental theorem of calculus to find the area of the region under the line y equals 2x plus 1 over the interval 1 to 3. All right, so you might recognize this problem. This is actually the first example we worked. Remember, we approximated the area under 2x plus 1 from 1 to 3, you splitting it up into 6 rectangles. We found the area of each of those rectangles and added them up. All right, but now what about if we want to find the exact area under this curve? Well, to do that, we've got area is equal to the integral 2x plus 1 dx from 1 to 3. So there you go. That's how you find the exact area under the curve. You just integrate the function and evaluate it from whatever it wants you to, from 1 to 3 in this case. And so this is going to be 2 times x squared times the reciprocal of the new exponent plus, and then the antiderivative of 1 is x, and that's going to go from 1 to 3. And so we get x squared plus x from 1 to 3. Okay. And so we are going to get 3 squared plus 3 minus 1 squared plus 1. And that's 9 plus 3 minus 1 minus 1. And that is going to give us 10 as an answer. See, I just went ahead, 1 squared is 1, and that's 1. I distributed the negative. That's why I've got the minus and the minus. So you can see it's pretty easy. This problem's easier than the ones we've been working. They put it in a word problem. All right, so what about this one? Find the area of the parcel of land that is described as the area under the curve y equals x cubed plus 1. Okay, that's how that area is described. It's that instead of having a rectangular area, this area looks like x cubed plus 1 from the interval 0 to 1. So I mean, if you look at that graph's going to look something like that, and 0 to 1, and so that land looks something like that right there. That's what we're finding. Okay, that area there. Okay, and it says if the land in the parcel is appraised at $12 per square foot, what is the total value of the parcel? All right. So actually, we need to find the area first. So let's do that. So we've got the integral from 0 to 1 of x cubed plus 1 dx. And so when we integrate, that's going to be x to the 4th times the reciprocal of your new exponent plus x, and that's from 0 to 1. And so that's going to be 1/4 times 1 to the 4th plus 1 minus 1 to the 4th times 0 to the 4th plus 0. And this is going to give us 1/4 plus 1, which is 5/4. All right, so just remember, well, let's read on in the problem. So over the interval 0 to 1, where x and y are in hundreds of feet, if the land in the parcel is appraised at $12 per square foot, what is the total value of the land? All right, so the area is 5/4, and remember, x and y are measured in hundreds of feet. So we've got to do times 100 times 100. All right, we got an x value and we got a y value. So the x is measured in hundreds and the y is measured in hundreds. So we got to multiply each of those values by 100. And so when we do that, that is actually 12,500 feet. Whoop, not feet. Well, not feet, square feet. So that's the area. And so if we want to find the value, so the value is equal to $12 times 12,500, which that's going to be $150,000. Whoop. All right. All right, so that was a pretty good problem. Now another thing you could have done is you could have taken the 5/4 and multiplied that times 12, and that would have given you 15. But then you would have to multiply that times 100, and that times 100. We're in square feet, and then this right here would have given you the 150,000 also. Okay. All right. Rules for definite integrals. Let f and g be any function continuous on a to b. Then we have the constant rule. So the constant rule, which says k times f of x dx, the integral of that from a to b, is equal to k times the integral a to b f of x dx. So what this is saying is we can just take the constant and we can pull it outside the integral. And we did that earlier in a problem. And then we've got the sum rule and the difference rule, just saying if we're adding or subtracting, we can split it up and integrate each term. Okay. And then if we integrate f of x from a to a, that's equal to 0. And then if we have the integral b to a and we swap the bounds, see if I put the b on top and the a on bottom, what that does is it changes the sign of the exponent. And then we've got a subdivision rule that says if we have the integral from a to b of f of x dx is equal to the integral a to c f of x dx plus c to b f of x dx, and c is some number between a and b. Okay. All right. Now, let's look at this example. It says, let f of x and g of x be functions that are continuous on the interval -2 to 5, and that satisfy this. Use this information to evaluate each of these definite integrals. All right. So you can see we're doing from -2 to 5 to f of x minus 3g of x. And we're going to use these properties up here to evaluate this. All right. So this is going to be -2 to 5 of 2 times f of x dx minus integral -2 to 5, 3 times g of x dx. And so this is 2 times the integral -2 to 5 f of x dx. See, I know what f of x is, I know what g of x is, and I know what this f of x is. All right. And so now, oh, wait a minute, I messed that up. That should be a 2 there. See, I just pulled the 2 out, and then minus, and then I'm going to pull the 3 out. -2 to 5 g of x dx. And let's see. All right. And so now we are left with 2 times, well, what is this? -2 to 5 f of x. Okay. All right, I actually copied this problem down wrong. You see this -2 to 3? That should be -2 to 5. Sorry about that. All right. I got to looking at this part right here, and I'm saying, well, wait a minute, something's not right. All right. So this is 2 times, now what does this equal? This equals 3. So that's 2 times 3 minus 3 times, and then what is this? That's -4. All right. And so then we can see this is 18. Okay. All right, let's look at the next one. And And to look at this next one, we're going to need all of this. So let's bring this down so we can see it here. All right. So I've got f of x, the integral negative 2 to 3 f of x dx. Now notice I don't have a negative 2 to 3 anywhere down here. But what I could do is I could write this. This would be, I could write this negative 2 to 5 f of x dx is equal to what? Well, let's look at this. I've got a 3 to 5. I know what that is. So what I could do is I could write this negative 2 to 3 f of x dx plus 3 to 5 f of x dx. Remember that this property up here that says we can break it up? If we have a number between a and b, we can go from a to that number and then that number to b. And that's all I did here. I just decided to break this one up at 3 because, see, I have a 3 to 5. And so what this does is this gives me 3 is equal to the integral negative 2 to 3 f of x dx plus, and then this one is 7. And so now if I subtract 7 to both sides, I get negative 4 equals negative 2 to 3 f of x dx. And there's your answer. Okay. This is after subtracting 7 to both sides. All right. So that's not too bad. All right. Net change theorem. Let's look at this. So it says if q prime of x is continuous on the interval a to b, then the net change in q of x at x varies from a to b is given by q of b minus q of a, which is equal to the integral a to b of q prime dx. All right, so let's use this to solve these next problems. All right, it says at a certain factory, the marginal cost is this, dollars per unit, when the level of production is q units. By how much will the total manufacturing cost increase if the level of production is raised from 6 units to 10 units? All right. So for this one, we're talking about cost. Well, what is marginal cost? Marginal cost is the derivative of the cost function, right? So that means this function here, that is dc, dq, which is 3 times q minus 4 squared. And so I can get the net change, or the net change in the cost, by using this formula here. So remember, we're going from 6 to 10 units. So I have c of 10 minus c of 6 is equal to the integral 6 to 10, and I'm going to pull the 3 out, q minus 4 squared dq. Okay, and so this right here, I will be using u substitution. So I'm going to let u equal q minus 4, du is equal to dq. So I can put the u in to q minus 4 and put the du in for dq. So this is going to be 3 times the integral u squared du. And what do we have to do? What did we learn? We have to change the limits. So I'm going from 2 to 6. And so this is going to be 3 times 1/3 u cubed from 2 to 6. And so that's u cubed from 2 to 6, which is 6 cubed minus 2 cubed, which that is $208. Okay. Just a word problem. I mean, this right here is pretty simple. Just integrating with, and you've got a definite integral here. That's all we're doing. So remember the problems we're working right now, these are definite integrals, and the ones we did in the previous 2 videos, those are indefinite integrals. They don't have the bounds on the integral. All right, let's look at this one. It says a protein with mass m grams disintegrates into amino acids at a rate given by this. So they tell us that dm dt is -30 over t plus 3 squared grams per hour. What is the net change in mass of the protein during the first 2 hours? So we're looking for the net change during the first 2 hours. Okay. So that's what? That's M2 minus M0, right? That would be during your first 2 hours. At hour 0 to hour 2. And so that's going to be -30. I'm bringing the -30 out. 0 to 2, 1 over t plus 3 squared dt. All right, so let's make a substitution. U equals t plus 3. du is dt. And so this is going to give us -30 times the integral 1 over u squared du. So the t plus 3 gets replaced with u, and the dt gets replaced with du. And we've got to change our bounds. So u is equal to 2 plus 3, which is 5, and u equals 0 plus 3, which is 3. So we're going from 3 to 5. All right. So now remember, to integrate this is going to be -30 integral 3 to 5 u to the -2 du. I'm just moving that up. I can use the power rule now. So that's -30. That's going to be u to the -1 multiplied by the reciprocal of -1, which is just -1. And that's going to go from 3 to 5. So this is going to be 30 over u, right? That's positive 30. And then move the u to the first down. And that's 3 to 5. And so that's going to be 30 over 5 minus 30 over 3, which is 6 minus 10, which is -4. So we get a -4 there. So we have what? We have a net decrease of 4 grams over the first 2 hours. All right. And that is all of this lesson. So I hope you enjoyed that. We learned how to do definite integrals with some good word problems thrown in there. So I do hope you enjoyed that. And if you would, give me a like, share, subscribe, and comment. And I will see y'all in the next video. Later.